Hi everyone. In this video we will cover the mean value theorem. The mean value theorem is used in a variety of applications both in Calculus 1 and in Calculus 2. In particular, and of most interest to us, it'll be the foundation of L'Hopital's rule, which we'll see a little bit later. Here is the statement of the mean value theorem itself. Let f represent a function that is continuous over the interval a to b inclusively and differentiable at the very least over the interval a to b exclusively. Then there must exist at least one value c that is found in the interval between a and b where f prime at c will equal the ratio between f of b minus f of a and b minus a. Now what does that mean graphically? So here is an example of a function that is definitely continuous from a to b, differentiable as well because of how smooth its variations are. The ratio f of b minus f of a over b minus a would represent, in this case, the slope of the secant line through the two extremities. What the mean value theorem implies is that we will always be able to find at least one point where the slope of the tangent line will be equal to the slope of the secant line through the extremities. In fact, there are many occasions where we might even find two such points between a and b where the tangent line slope is the same as the slope of the secant line through the extreme points of the interval. As an example, let's show that function f of x equals arc sine of x has a slope of pi over 2 at least once within its domain. A few reminders: arc sine of x is continuous over its domain, which happens to be from minus 1 to 1. F prime of x, which is defined as 1 over the root of 1 minus x squared, is defined as long as there is no division by 0, so x cannot be 1, nor can it be minus 1, and as long as the content of the root stays positive. So that's guaranteed for all values of x between minus 1 and 1 exclusively. So f prime is defined, in other words, f is differentiable on the interval minus 1 to 1 exclusively. F at minus 1, the left bound of the interval we're considering, is minus pi over 2, and the function's value at 1, arc sine at 1, is pi over 2. So according to the mean value theorem, which allows to be used as long as we have continuity from minus 1 to 1, inclusively in this case, and differentiability from minus 1 to 1, despite the fact the bounds are not differentiable themselves, it's still acceptable. So the mean value theorem predicts that there should be at least one moment between minus 1 and 1 where f prime at c will equal the secant line slope through the extremities, which in this case is a slope of pi over 2. And that proves the criteria we were trying to demonstrate. Graphically, here's what we've done. We have our arc sine function. As you can tell, it is continuous from minus 1 to 1. It's differentiable, so smooth between minus 1 and 1. At the bounds themselves, differentiability is not satisfied because both the curve starts vertically, so vertical tangent line, ends vertically, vertical tangent line at the extremities, but that's okay. Mean value theorem doesn't necessarily oblige the extremities to be differentiable. The slope connecting the extremities is pi over 2, and as we can see from the graph, there are two distinct points where these tangent line slopes will be the same as the secant line slope. As a second example, we're going to show that the function that is shown above, x cubed minus 4x squared minus 7x plus 12, has at least one stationary point between x equals 1 and x equals 5. A reminder that a stationary point occurs when the derivative of a function is 0. So We could translate this question into saying, show that the function has a slope of 0 at least once, between 1 and 5. To be able to apply the mean value theorem, we have to check that its conditions are respected. So there is one thing that's for sure, this function is continuous over all real numbers since it is a polynomial, and therefore it is also continuous on the interval 1 to 5. The function's derivative, 3x squared minus 8x minus 7, is also a polynomial and is therefore also defined and continuous on all real numbers. This means that function f, since its derivative is defined everywhere, is definitely differentiable on the interval from 1 to 5. Furthermore, calculating the function's value at 1 will give you a result of 2, and calculating the function's value at 5 is also equal to 2. So as a result of the mean value theorem, we can anticipate that f prime at some point between 1 and 5 will equal 0, since 0 is the slope of the secant line through the two extreme points we have. And therefore, there is at least one point where the function is stationary within the interval 1 to 5 exclusively. Here's a graph of this function. F at 1 is equal to 2, and so is f at 5. And therefore, the secant line through the two extremities has a slope of 0. And as you can see from the graph, what the mean value theorem predicts is actually taking place. There is at least one stationary point between 1 and 5. And that value of c doesn't have to necessarily be found, but we know that it exists. This last example is actually an application of what we call Rolle's theorem. Rolle's theorem is really just a particular case of the mean value theorem when a function is continuous over an interval a to b inclusively and differentiable between bounds a and b, and if over more the value of f at a and at b are the same, then the mean value theorem still applies, and the fact that the function's values are equal at the extremities means that f prime at c is not equal to the slope of the secant line, which has an arbitrary number, but in this case would simply be a secant line of slope 0. So Rolle's theorem basically can help predict the existence of stationary points when 2 points of the function are known to be at the same